All right, lesson 2.4, linear functions and models. So what this is we're going to take linear functions most specifically, okay, just graphs of lines, and different types of ways that we can use linear functions and models to represent real-world situations. There's going to be a lot of graphing calculator work, okay, it's all going to be on the graphing calculator, so please make sure you have a graphing calculator to do this. Also, there is a handout that goes with this lesson. So if you did not get a handout in class, right now I would strongly suggest going onto Blackboard and printing out the 2.4 lesson handout before you watch the video. That way you have the information in front of you when you're going through the video and you don't have to write a whole bunch of stuff down. Also, the handout has all of the calculator commands on it so that you don't have to write them all down for yourself. Okay, so make sure you have that handout and a graphing calculator. Our learning targets for this lesson, we're going to use a graphing calculator to work with applications of linear functions and use a graphing calculator to find the line of best fit of a set of data points. All right, starting with linear model applications. So just as a refresher, we've already talked about this a little bit this semester. A linear function is in the form f of x equals mx plus b. Okay, or in other words, y equals mx plus b. That is a linear model. That's what we're going to be working with today, lines. Okay, so starting with a little application of linear functions. So when we're reading a word problem, okay, read through it once, just to read it, to see what it's all about, then go back and reread it to kind of get information from it. Okay, so we suppose that a company has just purchased a fleet of new cars for its sales force at a cost of $28,000 per car. The company chooses to depreciate each vehicle using the straight line method over 7 years. This means that each car will depreciate by $4,000 per year. This can be represented by the following function. V of x is equal to negative 4,000x plus 28,000, where x represents the number of years. So we have a company, so a car company just purchased a whole bunch of new cars. Okay, so we're going to go through again and kind of look for the important information. $28,000 per car. Okay, so that is where we get our plus 28,000. Okay, each car is worth $28,000. So each company, or the company, is choosing to depreciate each vehicle. Okay, and when we say depreciate, that means the value of the car is going down. Okay, using the straight line method. Okay, so the straight line method, that just means it's going down in a straight line. We're going to have a linear function. Okay, it's going down by the same amount every single year. So each car will depreciate or go down in value by $4,000 per year. So this is why our slope is negative 4,000. Okay, every single year it goes down by $4,000. Okay, so this is our function. Okay, x represents the number of years, which means our v of x is the total value of the car after however many years. So v for value. So after X amount of years, what is the value of the car? So A says to graph the linear function using the window y is from 0 to 3,000 and x is from 0 to 10. Okay. So we know our y value, all of our cars start at $28,000 per car. So our y value is not going to go over 3,000. Okay, it starts at 28,000 and goes down from there. So we set our y window at 3,000. The car is never going to be worth negative value. So it just starts at 28,000 and then goes all the way down until it's worth nothing. But we're never going to have negative. So our range is from 0 to 3,000. Okay, x is talking about the number of years. Okay, x is the number of years. So for our domain, we said maybe from about 0 to 10 years. Okay, usually that's how we look at a car and the value of it for the life of a car. Okay, so we wouldn't want to say like 1,000. We wouldn't even want to say 100. Okay, it's not reasonable that somebody's going to have a car for 100 years. Okay, so we look at the value in the years in a reasonable amount of time frame. So about from 0 to 10. Okay, so part A says to graph the function. Okay, so with your graphing calculator, we are going to put in negative 4,000 x plus 28,000. And again, our window, okay, the x, the number of years, goes from about 0 to 10. That's the average life expectancy for a car, about. The y minimum is 0, and we can't go over 3,000.
Everhart, please report to the front office. Jackson Everhart to the front office.
Okay, so let's double check this really quick. Negative 4,000x plus 2,800. Our window from 0 to 10. Oops, I forgot a 0 here, so 30,000. Okay, I'm going to count by thousands. Okay, makes sense there. All right, so here we have the car depreciating $4,000 per year. Okay, and after a certain amount of time, the value of it is just going to be 0. So there's our graph. So part B says find the book value of each car after 3 years. Okay, so the book value is going to be the V, okay, the Y. Okay, so after 3 years, which is our X value, oops. Okay, so 3 years is our X value, so we want to plug that in and find our Y value. Okay, so if you go back to your calculator, if you go to second calc, that first option there says value. Okay, so what that is I'm going to tell the calculator which X value to plug in, and it's going to give me the output for it. It's going to tell me what my value of the car is. So choose option 1, and you said X is 3 years. Hit enter. Okay, finds that point on the graph. So Y is 16,000. Okay, so the book value of each car after 3 years is going to be $16,000. Okay, so it depreciates quite a bit. It went from $28,000 to being only worth $16,000 after 3 years. Okay. Part C, when will the book value of each car be $8,000? Okay, so that is going to be, so the book value, we said that is our Y value. Okay, that is the output. That is what we're trying to find. So we're given $8,000 for our Y value. So we plug that in. 8,000 is equal to negative 4,000x plus 28,000. Okay. So we're finding when will the book value be. So when we're solving for x, solving for the amount of time. So subtract 28,000 from both sides, and we get negative 20,000 is negative 4,000x. Divide by negative 4,000. So we get 5 years. Okay, so after 5 years, the value of each car will only be $8,000. Okay. All right. Next one we're going to talk about is equilibrium value. So we heard the quantity of a good is the amount of a product that a company is willing to make available for sale at a given price. The quantity demanded of a good is the amount of a product that consumers are willing to purchase at a given price. Suppose that the quantity supplied, S, and the quantity demanded, D, of cell phones each month are given by the following functions. Okay, so first let's talk about what this means. So we've got a cell phone company, and they're producing cell phones. They need to keep track of how many people are buying cell phones. Okay, that's the demand. Okay, so the quantity demanded is the amount of phones that the customers are willing to purchase. Okay, so they collect data over years and years and years of selling cell phones to figure out what is the demand. What do people want to buy? Okay, so that is given by this function here. Okay, so the quantity that they're willing to make available for sale. Okay, so the quantity supplied is how many they're going to make. So they need to be able to keep up with, okay, the quantity that they make needs to be kept up with the quantity that is demanded, what the people want to buy. Okay, and it's a nice balance. Okay, you don't want to make too many cell phones, then not enough people buy them. Okay, if you don't make enough, then that's going to be a problem too. Okay, so here is the supply equation. So we need to be able to, as a cell phone company, figure out what that good balance is. So we're going to start by graphing these functions on the same graph. So we have our window, x is from 0 to 100, okay, or in other words, that's P. So that's our price. So the given price is going to be P, here and here. That is our x value. Okay, so we're going to look at from about 0 to 100. Okay, about around what these cell phones might cost. Then our y value, okay, is either the supply or it's the demand. Okay, so we have supply depends on price and demand also depends on price. So graphing them on the same axis, so in our calculator, we have 60p, which we're going to do x in the calculator, minus 900, negative 15x plus 2,850. So that is your supply versus your demand. Our window goes from 0 to 100. I'm going to count by tens. And from 0 to 3,500. So we could probably count by hundreds for that one. Okay. So graph that. Remember, we're working with linear models, so both of these are going to be linear graphs. So I have my supply and my demand. So supply is going up, you make more and more and more. Demand, your demand is going up, it's down, and your supply is going up. So you keep increasing your supply, it looks like demand is going down. Okay, so, oops. So what we want to do is find the equilibrium price. What that is the price at which the quantity supplied is the same as the quantity demanded. Okay, so you make the perfect amount of phones so that you make just as many as people want to buy. That's the equilibrium price. What price could I set my phones at so that I do not have any extras? Okay, so our goal here is to figure out a good price. We don't want to make our phones too expensive because then the supply is going to be more than the demand. Okay, let's go back to our graph a little bit here. Okay, the demand is going down because as the phones get more expensive, less people are going to want to buy them. Okay, so we want to figure out where is the perfect balance. So if you go to second calc, okay, so looking at those black directions in the black box, second calc, now we're trying to find where they're equal. So we're trying to find that intersection point. So that is option 5. Okay, first curve says, so all you want to do is make sure that your cursor is on one of the lines. Okay, so you hit enter. Then the second time around, just make sure your cursor is on the other line. Okay, so my cursor is on the other line that I have up there, enter. Okay, just hit enter again, and it finds the intersection point of those 2 points. So again, an x value is 50 and a y value of 2100. So let's remember, what was the price? The price was our x value. So when they're going to be equal, when I can have a nice equal balance between supply and demand, is if I charge $50 for my phone. That's going to be my equilibrium price. That was my x value when the supply and the demand were the same. Okay. What is the amount supplied at the equilibrium price? Okay, so that was 2,100 phones. Okay. So the supply and the demand was the same. We make 2,100 phones and we charge $50 for them. Okay, that's going to give us the best equal supply and demand. Okay. All right. Label the equilibrium price and quantity on your graph. So here you should have sketched the graph when we graphed it. Okay, we're going to label this went from 0 to 100 and from 0 to 3,500. Okay, and we had a graph that looked like so. Okay, so right here is your equilibrium point where the price is $50 and the amount of phones we make is 2,100. Okay, right there at the intersection point. So determine the prices for which quantity supplied is greater than quantity demanded. Okay. So remember, going back to our equation, quantity supplied was 60p minus 900, and quantity demanded was negative 15p plus 2,850. So we wanted to know when our quantity supplied is greater than our quantity demanded. Okay, so let's look back at the equations again. So 60p minus 900 was the supply. That needs to be greater than negative 15p plus 2,850. So we want to figure out what is our price that will make this true, the supply greater than the demand. So solve for our price. So 75p minus 900 is greater than 2,850. Add 900 to both sides, so 75p is greater than, adding 900, so 3,750. Divide both sides by 75. Okay, let's do that in the calculator really quick. So 3,750 divided by 75, and you get 50. Okay, so we know that the price has to be greater than 50. That's when the quantity supplied is greater than the quantity demanded, which makes sense because $50 was when they were equal. So if we go anything higher than $50, we're going to have a lot more supply than we do demand. Okay, people are not going to want to buy the phones for this particular phone. Okay, this may not be an iPhone or anything smartphone like that, but for this particular phone, people will not buy it. It's not worth it to them if it's more than $50. Okay? All right. So, linear model applications. In baseball, the on-base percentage for a team represents the percentage of time that the players safely reach base. Okay, so they're on base. They safely reach base. The data given in the table represents the number of runs scored, which is Y, and the on-base percentages, which is X, for teams in the National League during 2003. Okay, so again, our on-base percentage okay, which is our X value. That's the percent of times that a runner gets on base. Okay, so over the whole 2000 season, for example, Atlanta had 34.9% of their players get to base safely. Okay, first base at least. Our Y value then is the number of runs scored. Okay, so Y value. So we want to know, okay, so we're trying to compare if 34.9% of our players reached first base safely. Okay, does that have any correlation with the number of runs that were scored throughout the entire baseball season? Okay, so how does the on-base percentage compare to the number of runs scored in our season? All right, so here's where we're going to have our graphing calculator. And you're going to need, this is where a handout will come in handy because you're going to need that data, that on-base percentages and the runs scored. And you're going to need the directions in front of you. Okay, so in the black boxes is the directions for your calculator. So we're going to enter in that data. So first one, to enter the data, you hit the stat button, okay, which is underneath the delete button. And make sure that your edit is highlighted, okay? And then hit option 1 for edit. Make sure your lists are cleared. So if you need to clear your list, just arrow up. So your list L1 is highlighted, hit clear and enter. Then you can arrow over, back and forth, however you need to. Arrow up so it's highlighted, hit clear and then enter. Okay, so your lists are cleared. You should have L1 and L2. So L1 is usually X. So type your data into each list, putting your X's into L1. So looking at your data, okay, so let's go back to our data on there, or if you have your handout and you're looking at it, that's fine. Okay, there we go. Okay, so put our data. So for X, we have 34.9. Enter. 35. Enter. Okay, 34.4. So I'm putting in all of the X values, all of the on-base percentages from both tables. Make sure you're doing it in order. Okay, then once you have all the X's put in, you need to put all the Y's or the runs scored into your list 2. Okay, make sure you go in the same order because you need to have corresponding X and Y values right next to each other. And be careful that you're putting them in correctly. Okay, so you should have the same amount of list 1 values as you do list 2 values. Okay, so going back to our directions here. So after you type the data into each list, we're going to create our scatter plot. Okay, so we've already done enter the data. Now we're going to create the scatter plot. So you go to Y equals, clear out anything that you have. Use the arrows to arrow up and highlight plot 1. hit enter. Okay, that turns our plots on. So you want to make sure that your plot is on. Okay. Also, you could go into second stat plot, which is above the y equals, and turn it on. Also, make sure you're on plot 1, it's list 1 and list 2, since that's what we put it in. Okay. Going back to your y equals, we're going to hit zoom 9. Zoom and then hit 9. And there is your scatter plot of all of your data points, looking pretty linear. Okay, so it looks like there's a pretty strong correlation from on-base percentages and the runs scored. Okay, so if a team is getting their players to first base safely more often, they're probably going to have more runs scored. Okay, so we have that nice linear model there. Okay, so the next thing we're going to do is find the equation for the line of best fit. Okay, the trend line, which usually in like Algebra 1 you do by hand, but we're going to have our calculator do it. So first thing, choose a linear regression model. Okay, so we're right here. Oops. Choose a linear regression model. So we're in that second black box following those directions. So you're going to go to Stat, arrow over to the right, so Calc is highlighted. We're going to pick option 4, line reg, because we looked at our scatter plot and it looked like it was linear. So we want to use the linear regression model. So that is option 4. Okay, hit enter. So list 1 and list 2 is what we're using. So you can just hit enter, enter, enter till you get to calculate and hit enter. Some of your calculators would do it and some of it won't. Some of you, just when you hit enter, you'll see this screen, which is fine. Okay, so it's in the form y equals ax plus b. In this case, a is the same as m. That's our slope. And they tell us that our a value, our slope is 62.17, and our y-intercept is negative 1,315.53. Okay, so that's what we're going to put in for the equation for the line of best fit. So f of x is equal to 62.12, or 62.17, and negative 1,315.53. Okay, so if you have your handout, go ahead and put that in for the equation for the line of best fit. Okay. So once we have the equation for the line of best fit, then we can go ahead and use that to predict the number of runs they scored during the season. Okay. So we're going to graph. Oops. Okay, so we're going to graph the line of best fit. Okay, went too far a little bit, so we're still here. Okay, we need to graph the line of best fit and then use it to make some predictions. Okay, now there's two ways you can graph the line of best fit. You can just go into y equals and enter in that equation, okay, that you wrote down. Or the calculator, there's a way you can put in the exact equation so that it's as accurate as possible, so there's no rounding or anything. So follow those directions there. You go to VARS, option 5, which is statistics. We're looking for our equation that we made, so arrow over to highlight equation. Option 1 is reg equation, and then hit zoom 9. So you have a scatter plot, and it'll graph it right there at that line of best fit. Okay, so what that VARS did is it put in the equation exactly how it was into your y equals. Okay, and then you can graph it with your scatter plot. Okay, so we're going to use that to predict if a team had an on-base percentage of 34, predict the number of runs they scored during the season. Okay, so again, on-base percentages, those were our x values. So we're going to do the same thing that we did before. Go to second calc. We're looking for, we're going to give a value for x and find the corresponding y value. So I'm going to put in 34 as my X value. And using my line of best fit, I can estimate, I can guess that if a team has a on-base percentage of 34% in a season, that they'll probably score about 798 runs. Okay. So that was just a prediction. Using the data that we had, drawing the line of best fit, we can estimate that they might score around 798 runs. Of course, we will never know for sure, but based on the data and the trends that we saw, that's a prediction we can make. Okay. So what if we're told how many runs they do score in a season? What might have been their on-base percentage? So now we're going the other way. So we're told how many runs they have. Okay, that was our Y value. So we need to figure out the on-base percentage, which is our X value. So plugging in 760 for Y into our equation that we have, and solving for X. So in that case, I'm going to add 1,315.53 to both sides. And we get 2,075.53 equals 62.17x. Divide by 62.17, and you get 33.4. So if they scored 760 runs in a season, you can estimate that they might have had around a 33.4% of on-base of an on-base percentage. Okay, so probably their runners got to base safely about 33.4% of the time. Okay. All right. And that is everything I got for you for using our calculator and linear models to make some predictions and work with some real-world applications. So we'll do a whole bunch more practice with that in our next class. So I will see you guys next time.